everyone. Thank you for attending this webinar hosted by Digital Twin Consortium and GE Digital. It is my great pleasure to introduce our speaker today, Dr. Colin Parris. As GE Digital's Chief Technology Officer, Dr. Parris leads teams that work to leverage technologies and capabilities across GE to accelerate business impact and create scale advantage for digital transformation. He also champions strategic innovations and identifies and evaluates new breakthrough technologies and capabilities to accelerate innovative solutions to solve emerging customer problems. Dr. Parris creates and leads the Digital Twin Initiative across GE and is a board member of the Digital Twin Consortium. Without further ado, Dr. Parris.
Thank you very much. So what I'm going to talk about the digital twins but from the perspective of delivering business value. Not only will we talk about how digital twins deliver value in the energy transition, but also how do you sustain and scale that value? And to show that, I've actually taken a certain aspect of industry. This is the part of industry related to energy transitions, and talk about it. How are we going to move to clean energy sources and do so in a stable, affordable manner? So with that, could you move the slide for me, please? So what I'm going to do in this talk here is I'm going to talk about a couple of things. So here's the flow. I'm going to talk about the market forces right now that are driving the energy transition at this time. You know, what are those things that are motivating this action? And then how do digital twins actually play in that? There's some aspects of that would make sense to you. Then let's figure out how to identify business value. That's the next topic. Then once you've identified business value, how do you capture business value? Now, business value is only captured when you take that digital capabilities of the digital twin, and then you find a way to embed that in an altered business process. Unless you can alter the business process to make powerful use of the digital twin, you're not going to be able to capture, sustain, and scale that value. Then what I'll talk about is actually in this new this new energy transformation, how do we think about the right set of digital twins that could allow us to actually capture value using this process transformation? So that's the flow. Look at the motivations, talk a bit about the business value they deliver, how do you capture it by process transformation, and then how do you accelerate it in the energy transition? With that, please go to the next slide for me. So let's talk a bit about the forces that are driving this energy transition itself. And so I have 4 listed there. You may find more. But the notion is the first starts with decarbonization, right? So we want more clean energy sources. And so many of those are renewables, whether it be wind, whether it be solar. You know, there's also hydro. That's a form of renewable capability we have. And many companies are now stating their carbon neutrality. You know, I will be carbon neutral by 2030, 2040, 2050 to certain degrees. And so that's a massive force motivating us. Second is this notion of electrification. Now, while decarbonization and renewables growth is talking about the different sources of energy that will be created, electrification is all about the sinks, you know, where that electricity goes to, people who use it. And so we see a significant rise in the electric vehicles, electrified homes using heat pumps, a number of other things that are going to be using or sources of that electrical growth. Then there's this notion of decentralization. What that refers to, normally we have centralized power generation. You have these large combined cycle plants, large coal plants, large nuclear plants, and it's all sent from a transmission to a distribution grid to consumers, people who use it. However, right now in the distribution grid, you have people who are also generating their power and consuming power. Think about residential homes with solar panels on the roof. Think about industrial sites that are now adding wind farms and are adding batteries so that they can actually become more green, because they too have carbon neutrality targets. They can not only use electricity, but they can generate it as well. So that's a decentralization. And that's all these microgrids, virtual power plants, distributed energy resources. And finally, another massive market force is this notion of digitization. We have many more devices and sensors connected so we can get the state. Now, when you think about all of these things, think about the underlying sort of mechanics. There's a lot of dynamics in the system. So there's dynamics in that you're adding renewable sources, and renewable sources, are based upon the wind and the sun, which can vary. There's a lot of dynamics there. There's dynamics in electrification because people are adding new electrical vehicles. They're putting on solar panels on their roofs. Companies are adding wind farms to give themselves, more green power. So there's dynamics as these things get added there. There's the dynamics in decentralization because not only on the distribution grid can I actually use electricity, but I can generate it. So at any given point in time, I could be handing back to the grid. That's a dynamic. Then there's dynamics even in the digitization because, again, there's cyber concerns that you have. So there may be situations in which through malfeasance or mistakes that these things go down. Then I can add on top of that dynamics with the weather. So there's a lot of dynamics, and that dynamics is running on a base that is extremely stable. And when I say that, I'm thinking about if you look at these combined cycle plants, these gas turbines, they have a life of about 35 years. Wind turbines, 25 years. Many of the grid hardware pieces have been around for 30, 40 years. So imagine all of those dynamics on top of something that's extremely, constrained. And not only is it constrained physically, but it's also constrained with a number of government regulations as well as a number of financial commitments. So in the face of those dynamics and constraints, you have to find a way to deal with that, and a perfect environment for the digital twin to actually handle the complexity of the situation with the dynamics and find ways to give you an insight into early warning of problems, understand what we could predict, and understand what we could optimize. And why I think about this all the time is because I'm part of GE. And in GE, we live in this world. 1/3 of the world's electricity is generated in some form or fashion by our generators. We also have grid software in which 30% of the electrons on the planet flow through that software. So we see this in spades. So if you think about those dynamic forces in this constrained environment, how do you think of business value? So if you go to the next chart. So what you look at is, what are the ways you can use a twin to deliver value? And there are really three things we think about. Can I get early warning on a problem such that I can take an action so that I don't have, significant adverse consequences? Can I either predict the remaining life on a part or a component on a system, or predict a drop or a potential opportunity to increase performance? And then can I actually do some form of optimization? Can I optimize so that I can have the lowest cost electricity with the lowest carbon that's the most stable? So those are the things we use digital twins for. So let's talk about sufficient early warning. What we're doing here is we have a hydro plant, and in the hydro plant, we're trying to figure out when there will be cavitation. The air bubbles that collect, these things cause vibrations. Vibrations damage the bearings. So how could we build a twin, which is what we've built, using some of the design knowledge, manufacturing, and servicing knowledge, and then combining that with a significant amount of time series and other data to actually give me an anomaly score to alert me to when I should be getting early warning on a problem that could be vibrations that would damage the bearings. And you can see here, we can talk about how much, if you can do that early detection, that we can estimate that's $100K savings. Second is life prediction. How can I look at a combined cycle gas plant? Because I'm using these things. These things were built and meant to be turned on and operating at the optimal maximum capacity. But now that you've added renewables, right, and renewables are variable. Some days the wind blows, some days the sun doesn't shine as much. You have these combined cycle plants now operating in a cycling fashion. They're not always on, they're not always off. So that causes damages to the parts. How do I maximize my profit while minimizing the damage to the parts? So I've got to predict the damage on the parts as I cycle these things up and down. In performance prediction, the wind is extremely dynamic. A wind turbine stands 300 feet in the air, and each foot from the ground, the wind speed is different. The wind speed is different at different times of the day, each hour in the day, different times of the year, different based on weather. How do I understand that wind that's blowing and then alter the pitch and the yaw of the turbine itself so I can have the maximum energy created? And finally, the grid itself. How do I forecast the potential generation based upon renewable sources and the demand and balance it in such a way that I can get the best energy at lower cost, trying to buy that energy a day ahead, and then in some cases, maybe 15 minutes ahead. So these are the ways you actually extract value. Now, if you go to the next page, now, because you can attract value, right, it doesn't mean you can sustain it or do it at scale. So what we do with the digital twin is we have two cycles. We have one cycle around the twin itself, in which we're spending time building that twin, validating that twin. Does it deliver the value? You know, testing that twin. Does it run in all these different scenarios? Verifying that twin. Is it compliant to all the government compliance and other compliance you have? And then you deploy it. But when you deploy a few pilot programs, you know, you tend to use the data sources you already have. You tend to put it on servers that you already own. You tend to use access to analytics and teams that you already have present. Marginal cost. But if you want to do it at scale, not a pilot of 10, 20 turbines, but 3,000, 4,000 turbines in a broad fleet, you've got to think through that. Do I need dedicated server resources, dedicated people? So you've got to think through the scale aspect of it. How do I protect that data? Then how do I manage? What if that model drifts? What if the data drifts? What if this changes in the environment significantly? How do I learn and adapt in all of these cases? So that's a digital twin cycle, right? Building, deploying, scaling, and managing it. And that gives you insight. But now you've got to put that insight into a business process. For instance, let's talk about that wind turbine. Two processes. The first one is I'm detecting the wind is changing. I want to change the set points so that I can change the pitch and the yaw, the direction, as well as the tilt. And from that, get more power. How do I do that? So usually it goes to a command center. Somebody sees these are the new control set points. They put in a request. Either a person goes out there and adjusts it, or you can actually directly send that request in via remote capability and you adjust the turbine. Then that's an action you're taking. So from that insight, you take an action. From the action, you get an outcome. Do you see more energy being generated for the next week or two? If that energy isn't significant, you go back, you get that feedback and you change it. So that's the business value cycle. That's one cycle. The second cycle is maintenance. Now that I have this thing operating the right way, I would love to figure out how do I actually maintain it in an optimal way so I can have it running as much as possible. So think digital twin cycle, which is the digital insight, and then think business value cycle, which is changing the business process so that you use these things to deliver value. So if you can go to the next slide. The next slide, we in GE have spent a lot of time looking at those capabilities and trying to determine how can I formalize the ability to take a digital twin at scale and then change a business process such that I can deliver value. And I can do it in a sustained manner, right? Because I get better and more accurate, and I can do it in a scaled manner. I can do it to more and more capabilities. And we have this process we call Lean+Digital. So Lean is the process we use for business transformation, and digital is the process we use for getting digital insights. And the combination of the two delivers both better value to customers as well as better margins to us, allowing us to invest more in digital twin capabilities to deliver more value for the customer. So this is a complex chart, but I'm just going to give you the essence of it. So let's start on the left-hand side. In the left-hand side, you have the Lean process transformation enabling the digital. What do I mean by that? Lean allows you to identify the top business problems you have. There are a variety of tools. PRPQ is a tool that says, this is the problem that's most likely taking away the most, it's causing the most waste in your process. And a process is, how do you go from starting to say you can deliver value to actually delivering it to the customer? Then I map, right? If you actually want you've identified the things that are taking out the most waste. What is the value stream map? Who does what when? I get this information, this person does an action, it passes on to this person in this process, this person does a third action, and at the end you get a result. That's a value stream map. We look at the entire value stream map, gather data from that map, get a benchmark, how long is it supposed to take, what resources, and then find ways to optimize that value stream. And we do that by something called structured problem solving. How do I understand the problem? Get the Pareto of the biggest problem. How do I analyze it with 5 whys or other tools? And how do I actually say, here's the way to get a solution? That's the left-hand side. And then what we do is we do the very same thing on the digital side. Instead of getting a process stream map, we get a data flow map. Where does the data flow from? What are the systems? What's the quality of the data? Is the data there in a timely manner? Is the data accurate? And then we combine those two. In the middle, you'll see this thing called a problem-solving or Lean+Digital process. I'm looking at the value stream map. I'm tying that to the data flow map. I'm understanding when we're making decisions on data that's inaccurate, or I'm understanding when we're making decisions in situations where we're not aware of what's going on, and I'm finding ways to provide digital insights, and then I'm changing the process to accept those insights. And that's the action plan. And in the end, what you have is this notion of digital enabling lean. Because by doing this the right way, I have a dashboard where I can see the flow of data, I can actually see the business value, and so I have a dashboard of business decisions. Then I can continually look at that stream of value I have, and I can learn from the data, ways to remove waste, identify new capability, and then I can use that constant stream of data to continually learn. So let's go to the next chart and give you an idea of what this is in real situations. So what I'm talking about here at a high level is that we have wind turbines in the field. What we're trying to do is that these are generating electricity. So what I'd love to do is I'd love to inspect them, especially the blades, and detect any problems on those blades very early. Because if I can, then what I can do is I can go and quickly repair them when the damage is small and when the repair cycle is short. And you see, if I leave that defect too long, I have to do something much larger. I have to do a much larger repair, and that larger repair, small repair might take me 8 hours or 10 hours. A larger repair might require a crane. Then once I bring the crane, I've got to wait for the right timing, because I can't send people up with a crane unless the wind is right. That may take 2-3 weeks. So I can actually do something with early detection of a problem in a day, or I can wait and it costs me 2-3 weeks. So what we do here is first initiate and perform an inspection. We use drones to inspect those blades. And those drones take pictures, and we use AI to actually look at that through computer vision and deep learning and determine, is there defects? Is there a crack? Is there a rust anywhere? What's the size of it? And then from that, we can get that data. That's the first part. Then from that, we have to generate an inspection report and dispose. What does disposition mean? Disposition means is when I look at that inspection report, I've got to decide what to do. So here we have a life prediction digital twin. We're going to estimate the severity of that defect, right? And we're going to actually use that. And we take data from that defect, but also data from the fleet. So it's a living, learning digital twin. And we think about it and say, what's the likelihood of this defect impacting our ability to deliver energy? So what's the trade-off between the annual energy that could be produced and the cost and the repair we should do now? And our digital twin predicts that and says, take an action. Go out there and actually make a repair. And then we actually go. We, again, monitor that to see that it's safe. We go and then we go replace the blade. Now, there's another digital twin there. We have a twin there that says we have to do 400 or 500 different repairs. Which are the ones we should do right away, given the damage? Because you need to understand the entire wind farm. Because based upon the energy generated by the wind farm, which of these should you do in priority so that you actually get the most amount of energy with the least amount of man hours and downtime to the customers? And this is a real life play in which every time we build a twin, we change the process by which people make dispositions or determine what to what to repair, as well as the way the workforce goes out and actually does the repair. Real life combination of Lean plus digital. Let's go to the next slide. So I've given you one example of how we integrate these pieces. Now I want to talk for a second in the energy transition and say, where are the most useful digital twins? I won't spend too long on this chart, but the notion here is that what you want to look for is those dynamics, places where things are changing rapidly, and with those changes, especially on a constrained base, where do I need to make complex decisions that the power of a twin can show you? And when you look at these, they're really around three big categories. The first one is this notion of climate and geopolitical. With the weather and cyber conditions, these are extremely dynamic. How do I ensure that the grid remains stable? Or if it does have to go down because of the storms, how do I recover as fast as possible? The other one is the end prosumer. With all the addition of the distributed energy resources, whether it be electric vehicles or people having their own solar capabilities or wind capabilities in companies, with the addition of all these things and this constant change, how do I have a twin that helps me understand when these things get added, how do I keep it stable? And then the last one here is all about carbon management. As people begin to understand the carbon requirements, how do I change? So if you go to the next slide, I'll tell you a bit about what we're doing. So we have a GE, a Digital Innovation Center, and what we have are three methods by which we begin to innovate and help transform and shape the energy transition. The first one is all about market pilots. Because to do this effectively, you have to look at the consumer, you have to look at the tier one utilities, you have to look at the government capabilities, you have to look at the market capabilities and bring these together. So we have three digital twin pilots going on. First one is focused on the transmission grid. How do I, when there are massive storms, understanding the age of the infrastructure, how do I determine which lines to de-energize so that they don't break and cause fires? And then re-energize. How do I turn them back on in such a way that you have the minimal disturbance? In other words, a minimal outage in that region. That's the first digital twin. The second is a digital twin of the distribution grid. When we have a significant amount of new additions, electric vehicles, how do I actually manage that grid such that not only do I have the grid stable, but I could actually use power that they generate to stabilize that grid. And then the third one is the combination. Now that I have, and these can only be used in certain situations. It all depends upon the structure, whether you're an ISO, DSO, TSO. How do I combine these digital twins of the transmission and distribution grid overall so I can optimize for stability, but also optimize for resiliency and affordability? While doing that as well, there are many other things we're pursuing from a technology exploration point of view. How do I do forecasting better with Humble AI and other twins? And then how do I use reinforcement learning? And then finally, if you think about this thing from a long-term perspective, how do I get the right partnerships with institutions and with the government as well, to fund as well as to bring in talent, in order to look at this thing at a high level? So why don't we go to the last slide? So what I've done is I've spent the time, really showing you the power that I believe digital twins have, that we believe digital twins have in GE, and the way that you've got to combine the process, the business process transformation with the digital twin capabilities. And then I've showed you a couple of examples that we can use in the energy transition. I'll leave you with two large thoughts. One is the notion of when you have this combination of process transformation and digital twin, what you're going to find is that you're going to get a constant stream of data because we have that in a large scale process. And you're going to get constant feedback on how well it's working, which gives you continuous learning and continuous business advantage. And that's what I think the aim should be, as we evolve these digital twins to take a meaningful role in our societies, helping us with these really complex problems. The other thing is, how do you sustain that advantage? Well, one way is improving the data. One dimension of data is the data that you collect directly, from the running machines. The other is the human domain insight. We have humans who've designed things. When we look at damage to the blade, if there's some things we can't detect, we actually have humans come and visibly look at it on the screens and then annotate the damage so that the machine systems can learn. So can I get those human domain insights and extract that expertise and then add that to the AI-driven data insights and give me more insight advantage? So if I have insight advantage and then I continually improve the business process, remove more waste, then I get continuous business advantage. And so this is the stream that we have using the digital twin cycle and the business value cycle to deliver value. And so I'll stop here. Hopefully this has given you some other thoughts. I'd love to get comments and a few questions if we have the time. Kayla, back to you.
Thank you so much for that insightful presentation, Dr. Parris. We do have time for one of our audience questions. So, how are digital twins making the electric grid more resilient to cyber attacks?
Yeah, that's a really good question. So the way we do that is we look at two things. One thing that the twin can do is, as I mentioned before, early warnings. They can give you a view of anomalies, right? So what you want to do is you want to look at an anomalous situation. You say, well, this hasn't happened. No, it could be because you have a failure of a sensor. It could be you have an unusual economic condition, or you could have a cyber attack. So the twins already give you that insight. And the earlier we can get that insight, the better. The second thing we have is we have something that we've been playing with called Digital Ghost. So Digital Ghost is a digital twin of an asset. So we can do a digital twin of the grid network itself. Now, what you can do with the digital twin of the grid network is the digital twin is a living learning model. If I perturbate that model, if I deliberately decide to take down, one or two small substations, that digital twin model will predict what should happen because it's obeying certain laws of physics. And if when I take down one or two substations, I see a reaction that doesn't look right, I can say, wow, that looks like an anomaly. Because again, if I took down the substation and I expected to see a drop in frequency or a drop in voltage, and there was a larger drop in voltage, it could really mean that something has happened to that substation or other substations around it. So we're using digital twins both to give us early warning as well as for us to actually, simulate, attacks on the network or change things on the network. And if you've changed things in the network and you expect a response and you don't see it, that's another insight that something seems to be wrong. And then you could actually determine which sensors or which areas, and then go isolate and more than likely mitigate that situation. So we are seeing digital twins help us here.
Amazing. Once again, thank you for attending. If you are interested in membership and benefits of Digital Twin Consortium, you can learn more at digitaltwinconsortium.org. Thank you and have a wonderful day.
Thank you.